So it's my great pleasure to introduce a speaker of the keynote presentation. We're very happy to have Professor Rolf Ernst from Technical University of Braunschweig, Germany here. He is the chair of the Institute of Computer and Network Engineering with more than 50 employees, covering embedded systems research from computer architecture and real-time system theory, also covering challenging automotive, aerospace, and smart building application topics. His research is or was funded by national and European programs as well as by companies, for example, BMW, Bosch, Daimler, Ford, General Motors, Toyota, Volkswagen, Intel, Siemens or Thales. He chaired major scientific events such as State or Embedded Systems Week. He was a member of the European Artemis Strategic Research Agenda team and served as an expert for the successor program EXCEL, as well as for Horizon 2020. He's an IEEE fellow, a Tate fellow, served as an ACM distinguished lecturer, and he's a member of the German Academy of Science and Engineering, ACATEC. He's a member of the advisory board of the German Ministry of Economics and Technology for entrepreneurship programs. And in 2014, he received the Lifetime Achievement Award of the European Design Automation Association. We are looking very much forward to his presentation, which is entitled Automotive Ethernet, Opportunities and Pitfalls.
Thank you very much for the very kind introduction, and thank you very much for inviting me to give this talk here about our research topic. And one of the important research topics in the last couple of years has been the use of networks together with scheduling of ECUs. And a cornerstone is the use of Ethernet. I will give you a quick introduction into automotive networks and show you why people are looking forward to use Ethernet in cars. They're already doing this now, but the use will extend over the next decade. There's not only the use for Ethernet as a simple infotainment communication mechanism, but also as a backbone for the whole system. I will explain what that means and give a closer look on the impact of on automotive design. Next, I will talk about the safety perspective, because this is something which is of high importance, because Ethernet has not been developed in the first place for that purpose. And finally, I will draw a little lengthy conclusion. So let me talk about the issue, why are people looking into the use of Ethernet in cars? There are mainly three trends. And here we have new infotainment applications. This is something which you already know. People have car-to-car communication or car-to-infrastructure communication. You download navigation data. You can download video data if you like. And there's a lot of communication going on in different purposes. Primarily, this traffic is of the characteristics of best effort. This is mostly seen, this development is mostly seen to the field of media infotainment, and many people are talking about that. However, there is a revolution going on in the automotive industry. There is more change and innovation than for the last couple of decades, and there are two reasons. The one is electromobility. This is a highly visible development, and with all the consequences for infrastructure and the shape of the industry. And the second are the driver assistance systems, which are now moving into a direction of autonomous driving. There are plans how to apply these steps of autonomous driving over the next decade. This has been much shorter than originally anticipated and is highly driven by American and other innovations. First of all, in the object detection, the capabilities of these features, and in the second, by promises of many companies to be able to do so, to utilize these. What is the consequence for us? We have a quickly growing sensor traffic. Now, this sensor traffic here brings higher resolution. Resolution actually goes up. It uses redundant image sensors. This is a very original one. Volvo has used a dual sensor radar together with camera to put these two sensor informations together to cope with bad weather conditions, with difficult scenes on the street, but only for single objects. And now things become much more complicated, where people want to work and to drive in traffic situations. And if you look at Asian countries, you know how difficult that could be. So redundant image sensors, which have to be coupled, which then means you have time stamping, you have all the coordination of the different sensors in the car. Here you have primarily high bandwidth communication, and what you would like to use is a switched high-speed network, because the current buses which we have are quickly run out of steam when it comes to these dimensions. This is different. We have a limited network latency. We can use timestamps to coordinate the sensors, but we have to make sure the sensor data are there on time. And this is needed to get limited system response time, which is of limited importance today, where you have still the driver in the responsibility, but of much more importance in the future, where the car will take more and more responsibility for the driving actions. So this is high bandwidth communication. Then next one here is complex low latency traffic for decision making, for control. This is increasing hand in hand with these two here. As soon as you use sensors of other cars, information of other cars, it's not only signal processing and control, it's increasingly so in the context of decision making, and also fail operational activities. So if you have an error in the car, it still must go on. So this means complex traffic, and this traffic is partly low latency. So one of the reasons for this, for the increase of low latency, is not only the sensor traffic, but also the idea to use these automotive networks as backbones for these requirements. Here you have legacy functions, future drives such as mobile electromobility, and here highly interactive functions where you use different functions to control each other, to check each other, and all this has to run in defined time. So this is a low to medium volume traffic, but it is low latency. Now, how can you bring all these things under one umbrella? And the idea here is, this is actually the birth of switch Ethernet. That might have been the incentive to look into the domain, the infotainment issue. But the real drive came from Trend 2. Please keep this in mind when I explain the consequences in the following. Now, why use Ethernet? You know that automotive traditionally has developed its own standards: CAN, LIN, MOST, FlexRay, right? Why would they do that? The reason is bandwidth, bandwidth, bandwidth. That's the main reason. You get these bandwidth for novel functions with these high data rates, and you can actually grow with technology from 100 megabit to 1 gigabit per second, which is now under standardization for cars, and next step will be 10 gigabit per second, and so on. So all this is possible, and you don't have to do that yourself. You have open network capabilities, because what you would like to go is you would like to go to open protocols such as IP protocols. There's another trend which is included in that one, and that's online diagnosis. You would like to diagnose the car, to communicate with the car when it is driving, such as Tesla is doing that today. You would like to do that on a higher level for most of the car functions. So this is something where you would also like to use the IP protocol also for techniques which have traditionally been separated from the open network, such as diagnosis. Shared technology cost is then the driver to go together with other people. So you don't have the cost of ownership to develop your own standards, even though you have a very high volume compared to, for example, industry. But nevertheless, it is much more efficient if you join forces and don't have to worry about MOST, FlexRay, and so on, which has always been a struggle between the different OEMs in the automotive domain, how to standardize these things and what the properties should be. You rather go on a larger scale. And there's a huge engineering platform experience in avionics, in industry electronics, has been used there for a longer time already, and you can profit from that, including hiring people from those fields. Now, this is also very good, but how can we efficiently design with Ethernet? This is now the question. It's not design with Ethernet, it's efficiently design with Ethernet. We have to make sure to control the costs. The costs have always been a major driver, much more than in other industries, when it comes to networking. That's the one point, but then if you design efficiently, you could certainly do that. You have already done this in office automation, but how can you reach the required safety under these circumstances? This is the big headache which people come up with, and I will go through the challenges here step by step. First of all, to understand what people have in their mind, it is good to see what the current approach is to automotive design. So this is bus-based communication. This is the standard today. And it is easy because it has a straightforward support of the publisher-subscriber mechanism, meaning one sender and many readers, which is found everywhere in the vehicle domain. There have been several application-specific standards which have particularly been developed towards the goals of the automotive industry. You see the examples here, and they range between something like 100 kilobit per second up to 10 megabit per second at the high end. Now, one of the characteristics here was a clear, predictable scheduling. So it was fixed priority on the one hand for CAN, or it was TDMA when it came to FlexRay, or you had a slotted ring here in this case, which was a MOST, which used the stream reservation. So all the predictability has always been a major concern here, and proof of safety properties has always been going hand in hand with this development. When it came to larger systems, and this is what you see in cars today, I can show you this simple abstract figure here. You have buses here, and they're connected to the electronic control units called ECU in cars through gateways. And what happens here is that the gateway is responsible for translating the protocols between these two buses. Gateways are, because of the slow speed here on those both sides, are typically developed as software gateways. So they have software functionality, software is adaptable, can easily cover different standards, so flexibility is there. People are adding more functionality into the gateway, advanced functionality such as the diagnosis is very often implemented there. This is where we come from. Ethernet, however, requires a major change in thinking for the automotive industry. First of all, it is a switched network instead of a bus. So it has point-to-point connections rather than bus protocols. It has a dynamic address handling, which people in automotive industry have not used so far. It has a different scheduling mechanisms. It uses flow control, which is so far only used in gateways, and it's always non-standard. Just as a side note, of course, Ethernet has originally been developed as a bus technology, but this is not suitable. You want the link-to-link properties. You have different communication schemes, unicast, multicast, broadcast, which can be controlled, different identifier assignments in the context here, so you just can use point-to-point identification and multicast, and, for example, addresses. And it is not primarily developed for time-critical communication. There have been additions like AFDX in the avionics industry, or time-triggered Ethernet, but originally that was not the case. And it uses complex multi-level protocol. And you have alternatives here. You can have many configuration parameters, and the overhead is higher than in CAN buses. So all these things are different to what people are used to in the automotive industry. The question is, what is the consequence for network properties and network design? First of all, to understand what is happening here, let's look at a very simplified architecture. We assume we have switches here for the switched network, and then we have terminal nodes, and we'll show later that many of those are actually gateways. Now, all traffic goes through these bidirectional links, and the reason is that this is the fastest and easiest electrical solution. So you can make it cheap and fast, point-to-point links. All arbitration, as a consequence, is done in the switches. So the switches now take the role of the bus protocol, and we have to focus very closely on what the switches are doing. And then, because of that freedom here, you can also have arbitrary network topology, so you can add more features like adaptable performance and redundancy, and adapt the whole thing to the individual car. Just to show you what people are using in the automotive domain, this is the so-called Open Alliance Protocol, originally developed by Broadcom and then licensed to, as a broader reach protocol. There's a simple two-wire physical medium. It's like a telephone wire. It doesn't even need to be shielded, and it uses different frequencies here to use the same link at the same time for different directions. So you have bidirectional link over two wires. Today we have 100 megabit per second. This is the standard which is used in the current automotive developments. And the nice thing here again is there's no link access arbitration necessary. Everything is done in the switches. There's another point which is new. Can messages have a fixed length? The difference is very minimum. It's between 0 and 8 bytes payload, right? It's minimum. Most of that is for headers and others. Similar for everything which you find in the environment of FlexRay, be it both the static and the dynamic part. So much of this is fixed. Here you have the very different sizes, 84 bytes to 1500 bytes, which you, for example, would like to use for camera frames. They are resulting link latencies if you don't allow preemption of frames. And here we get short frames here. The shortest one at 100 megabit are 6.7 microseconds. The longest one are 122 microseconds if you take the 1500 bytes. I should add that some of the automotive manufacturers currently don't like this. It's too slow, 100 megabits per second. They're already using in existing cars gigabit connections. But this is a trend which will be standardized later. Switch scheduling is very free. You have lots of opportunities. Weighted round robin was the original one. Then came static priority. I will talk about that in a minute. Time triggered, and you have different type of shapers which you can use if you would like to have real-time properties. And then there's the time-sensitive networking initiative consortium, which has defined a lot of real-time mechanisms to be able to use these kinds of Ethernet, for example, in the industrial domain, in avionics, and wherever. Let's have a quick screen of the standardization actions to better understand what I'm going to explain later. First of all, people are using standard Ethernet in the connection of 802.1q, which is a priority-based version, has up to 8 priorities and up to 4,000 virtual LANs, and it uses static priority scheduling as a primary workhorse. This has been extended with Ethernet AVB, the QAV, and is originally defined for studio applications in the video domain. So it is a streaming-oriented protocol. And this one here adds now a standard traffic shaping to the 802.1q. Right? And on top of that, it also provides clock synchronization, which is a nice thing. People didn't have that in the automotive domain outside FlexRay before. And now you can have the network itself can provide you clock synchronization so that you can use proper timestamps. This is something people very much appreciate. Then, last not least, the time-sensitive networking. Here, there's a set of Ethernet, part of them are draft, part of them are finished. Ethernet standards, they address real-time requirements. So this is the landscape we are talking about on the level of the link and the communication here. TSN adds more. Here we have frame preemption, which is important for us. It reduces blocking time by lower priority frames such that you can actually use long frames but allow to preempt them. So in the end, you get shorter latencies. This becomes necessary if you want to have short latencies. It allows preemption here of lower priority frames at certain points, but not hierarchically. You can only preempt from one level to another one, but not further down. So it's not arbitrary prioritization is possible. Then we have ingress filtering that ensures that traffic streams stay within their predefined bounds, and this, for example, helps in the case of fault containment. Timing and synchronization has been improved. There's time triggering. Very important here. There's a so-called timer where shaper with guards that allows low latency, time-sensitive traffic, so you can actually also mimic that kind of traffic if you would like to see that. And there are more shapers, peristaltic, burst limited, and so on and so on. Many more are showing up. The question comes up is how many of those are actually needed? The good news is that worst-case timing analysis is available for most standardized features here. We have been developing a PyCPA, which is a research tool for these kind of applications, which is scalable, and the commercial version of that, SimTA, is originally developed by and marketed through SimtaVision. There's also a talk on this time triggering preemption issue here in particular this afternoon by one of my students, Daniel Thiele. If you want to see that, it's session 3.1. This is only the lower level. Now there are more things above that which make it more attractive to use Ethernet. The one is you have an IP layer, so you have IP routing capability, and this way you get compatibility. This is what I said in the beginning. On top of that, above the layer 3, you have the layer 4, UDP or TCP. Both are supported. TCP has a disadvantage, has the advantage that it is the most used protocol, has the disadvantage that it requires handshake and flow control when you would like to communicate. So this is difficult to give guarantees under these circumstances. Therefore, people resort to using UDP, which is the connectionless protocol, also easier for publisher-subscribe applications, as we have it in the automotive domain, but possibly needs extra error control, right, which is not defined here. Just to give you an impression what that means here, you have the red box here is the Ethernet MAC layer, media access control layer. You have a lot of preamble, you have destination, source, the type of the network. Then comes the payload, and finally the control block. In the payload, you include the layer 3, which is here, with an extra header, and then into that one you put the TCP or UDP header. I show you that to give you an impression how much overhead you add by using all these extra elements, right? Extra layers, so you have more traffic than you originally had. You would have if you would, for example, use MOST. However, the advantage is here flexibility, and this flexibility and capability of integrating things is continued on the next levels. Some IP is a middleware, which is standardized the encapsulation of automotive data in TCP or UDP packets. And interestingly, while all services have been in the past fixed, so whenever you send message, you know exactly where you send it. It's designed at design time. Now with some IP, you can actually run a service discovery. Of course, you could do strange things, that if you turn the key, the system looks around, let's see, who is the motor here, right? But this is not the primary application for that, but applications where you would like to move services between different places. Right? So service discovery is new in such a way that it discouples the communication from the individual address and placement of the service. It has never been there in automotive. The next step then is the AutoSAR Ethernet socket adapter. AutoSAR is the automotive software standard which is used everywhere in the automotive industry. And like you heard in the keynote this morning, the high influence of the German industrial electronics on the rest of the world, here automotive software standard has always also been driven by German companies, but then with the help of Japanese, for example. Toyota is one of the first to enter the AutoSAR consortium. Now, the idea of AutoSAR is actually to provide a layer where you already have these services. So you communicate with another function which is sitting on another ECU, but you don't need to worry about how this is communicated and where this partner is sitting. So it gives a lot of platform opportunities in design. How can you use this in the context of Ethernet? Now, the software adapter here is embedded in the AUTOSAR COM stack, which was there before, adding all the features which you have seen before into that network, into that stack. And this achieves the compatibility to other communication standards in the car. So you would like to be able to run the same communication stack for Ethernet and for CAN and for FlexRay. The consequence is that this is more complex than in conventional bus systems. Let me show you just a quick view on what is on the AUTOSAR Ethernet socket adapter. You can read this yourself on the autosar.com. autosar.org, sorry, internet domain. They have all these documents there. Should be autosar.org. So the top here is the PDU router. The PDU router, PDU stands for Protocol Data Unit, gets the data to be communicated, the signal, whatever signal you have. It could be a signal from a transmission, a sensor signal. It could be a switch which is set. It could be a message from outside. And this Protocol Data Unit then has to send it to the right connector. So here you have an Ethernet. Here you have a FlexRay, for example. To do that, it uses here specific transport protocols. Here you have a specific adapter for FlexRay. I've cut out here the CAN, the LIN, and so on. What you need the socket adapter for, this is what is put in here, is to adapt this kind of PDU routing to the way Ethernet is using software, meaning to the AUTOSAR TCP IP stack. So you have, like in your PC, here you have embedded a TCP stack here. And this is similar. I've seen similar applications, approaches in industry communication. It means that you have TCP, UDP here, and the respective protocols embedded. From there, you go to the Ethernet interface or FlexRay interface, and then there's the standard approach to go to closer hardware. What you also see, which I've omitted now here, is a service discovery service, which has been added to also include some IP functions. So this, just from this picture here, and this is why I used it, you see that things have become more complex with using Ethernet. Flexibility is paid by complexity. Okay, so we have to be cautious here. Ethernet has many more parameters and variants than in current networks. You have MAC address management, private or public. You have switch management here, which can be run differently. The protocol selection, the packaging, everything is free. And you have to decide how you use it as an OEM or as a first-tier supplier. Now, the current standardization, and this is what we have to keep in mind, addresses the compatibility issue. Keeping Ethernet compatible between the different Ethernet standards, and for AUTOSAR and the automotive industry, keep this compatible, as I showed you before, between the existing architectures and standards, AUTOSAR, CAN, FlexRay, and Ethernet. So this compatibility and integration issue is the main problem which standardization currently faces. It does not limit, unfortunately, the variety which you can generate this way, and it easily leads to incompatibilities and inefficiencies, and in the end, costs. So we have to be cautious what we do here. Now, with that start, let me move on to Ethernet as a backbone, and I would like to give a closer look here. This is the idea which people have when they talk about Ethernet in the future. Basically, you have the CAN or CAN-FD, which is a successor standard to CAN. You go over a domain gateway here. You have some advanced driver assistant or automatic driving system. You have the powertrain over here. And you have another one, the FlexRay, for example, for chassis. And in between here, including the infotainment, you have a switched Ethernet as a switched network, and it serves all these different subnetworks. At least this should be possible. If everything is included this way, is questionable, but this is the way they are currently moving into this direction. I'll give you an example what that means if we would use such a network as a use case. So we have tried to evaluate how we could actually handle these different traffic types over one backbone network. And we use a use case from DMW for that purpose, which they have frankly published. It's an ECU with 4 control units only. It has 62 kilobits per second, which is streamed to the head unit. There are 4 cameras on front, side, and rear. Each of them has a compressed transfer of 26 megabits per second streaming to the head unit. And then there's a rear seat entertainment with audio and with video. And there's also internet traffic, bulk traffic, where people can surf in the car. So what we've done here is looked at the proposed technology here. That's one of the proposals they made also in that paper. You see here different switches. You see here the cameras, the front cameras, the head unit here. You see the audio video on the rear seat. You see the rear camera here and several controllers, control units, the ECUs, which are directly connected to the switch, and they have CAN properties. The traffic is defined. We used SIM-PAS, or more precisely PyCPA, for a worst-case analysis. And that's what you see here at this point. So this is the latency for all these elements. And we see here that we have from 0 to 12 millisecond maximum latency. And you see that the critical ones here, the cameras, for example, they are in the range of 2 to 4 milliseconds delay, while the bulk traffic, the internet traffic here is a bit slower, so it's less privileged. Okay, and here at this point we used Class B. The Class B traffic, which was used for the cameras, was done with 10% over-reservation with an AVB protocol, while the latency critical traffic from here from the controllers was run in Class A and with no shaper. So those are terminology of the AVB. TEFA was turned off here. So what you can see here as a result, that's one of the publications of recent publications here, how the whole thing depends on different topologies. Here you have a double star technology. Here you have the quad star technology, a line technology where all the ECUs are set in a line, and here finally a tree. And what you can see here for let me start first. The signals have a period of 5 milliseconds to 1 second, the control signals, but they have low latency requirements. What you see here at this point is that all of them, all these transport, even in the worst case, are less than 3.5 milliseconds, so they are in the range of the period. So there is never the situation that the next control signal comes before the first has been transmitted. And that means we don't need to pipeline anything in the topology, at least not here. It means that there's also no overwriting in the ingress transmit buffers. So that's big relief. We don't lose any packets here if transmission is correct. Situation looks different for the cameras, and the problem is here that cameras have a much shorter frame period because the large frames are built into smaller chunks of data which are then transmitted over the network. So I mean one big frame has lots of small communicated frames, and therefore we have a frame period of typically less than 1 millisecond. And if we look at the timing data here, we see that some of them are actually lower, but some of them are higher. Oh, this NO and not NO means the one is an optimized analysis and the other one is a non-optimized. That doesn't make much difference here. They are almost equal here. What you see at this point is that here is the period, the range of periods. This is the one here, and here's the delay time. So we are sure in this case that in the worst case we have to buffer frames, otherwise we are losing them. So that already tells us a little bit about the way we have to set up the switches. Now, what is the conclusion we can draw here? Now, first of all, high priority control traffic in class A seems to be okay, at least from this experiment here, and we have seen this in other places as well. Ethernet is fast enough with its capabilities to avoid overwriting in the transmit buffers, and it is therefore only a problem if there is not enough switch buffering. And this holds for all investigated topologies in the example here. For the high priority camera traffic B, we have the risk of overwriting, so we have to do stream buffering. It's not possible otherwise. And again, this also holds for all investigated topologies. So there's a difference here already, and which has an impact on the switch. On the other hand, we didn't need any shaper for class A, and for class B it seemed to be sufficient. So at least for these kind of applications, we don't need any frame preemption. We could do without frame preemption in these applications. Okay, so we see Ethernet could be a good backbone. We might need some extra switch design, but at least we are on a good path. But now the big question is the safety perspective. Let me first talk about how cars look today and where the safety problems come from. Of course, we have functional safety issues on the different functions here, for example, adaptive cruise control here at this point, and they use a lot of functions on different places of the car. So currently, what happens is that such functions have their own ECUs, and they run all these functions locally. If you go to autonomous driving, that will not be possible anymore. You have many different sensors and many different functions which you have to bring together over the network. And that means here at this point that we have to look into mixed criticality issues. So the ISO 26262, which is the automotive safety standards, requires that if over one network here, and today that would be a CAN network, for example, if messages of different criticality, safety criticality are transmitted, there must be freedom from interference. That means we need some isolation between these mechanisms. I'm not looking at all the problems we have in the CAN bus here, but I'm only interested in the Ethernet. So secondly, people have used this property in the past. And I give you an example for CAN messages. They used what was called criticality as a priority and gave higher priority to safety critical messages, such at least from the timing perspective, they could use for the safety critical messages worst case design, and then only assume these lower priority messages as blockers, and the blockers were always short. This is different now with Ethernet, right? They're always short, and for all the other ones, they used some other worst case, non-worst case design processes, such as simulation or so. So this is a standard approach people have been using today to reach the level of timing guarantees they need for safety. Now, this allows occasional loss of these lower priority messages without problems on the higher level. Now, there are mature solutions which are actually standardized, and there are comparable solutions for the other standards, such as FlexRay, which uses TDMA, that's another form of isolation, or MOST, which uses reservation. So this is what people are used to. Now let's look at Ethernet. How well does Ethernet actually isolate it critical from other traffic? That's a question we have to answer now when we use the system as backbone. We need freedom from interference also here. We also would like to know what happens for delivery under transmission errors. So what are the timing guarantees that are possible under errors? Right? And then the fail operational question. So how well can the network failures can be compensated? Now, first of all, let's see what people have been doing so far. Again, what you could do, if you would like to have the same effect as I showed for CAN, then you could use the general traffic and the time critical, and the critical one you can put to class A, and then you have the class B camera traffic, and then other traffic from the general traffic could go to lower priorities, such that you are not basically interfering the higher ones, and then you can use the same scheme as before in CAN. That is the idea, and similar ideas you can have for TDM. All right, TSN, FlexRay, and so on. But is this isolation really working? Are we answering the right question here? Now, let's have a look who is playing the role here. Now, I showed you this figure before, and now I'm concentrating on the switch. Because the switch has to do what we said. Does the switch really do that? Now, a switch here is not a software guy. The switch needs hardware support because of speed, and this will remain. There will be no full software systems implementation here because they are too expensive or too slow. And what you see here is the general building of such a switch. You have the switch fabric down here with the schedulers here for out egress schedulers and ingress stage here. And this is typically done completely in hardware. On top of that, and this is the interesting part, which is hardware accelerated in the existing switches, does packet handling. So packet handling uses memory here, and because of the speed here again, all the memory accesses here, and the forwarding of the packets here, the parsing and lookup porting, this is all done in hardware. So we cannot easily change that. And on top of that, you finally have the software switch management, which is all in software. So this is how a typical switch looks like. Now, when we would like to know what the possible consequences are, let's go through these step by step. First of all, this table here, the forwarding. The table here, which, sorry, I have to go one step back. This table here, which is the memory, contains the program data. The forwarding table, which says which address goes through which part. This is exactly one of the things which Ethernet switch does. And then the queuing buffers, which implement those buffers here. They are not dedicated hardware buffers, but they are typically in a large queuing buffer, or several large queuing buffers. So let's go back to that one. First of all, the indexing space here, you will see that we can lose timing through the forwarding table to physical limitations, and that means here interference. The queuing buffers have a limited buffer space. There could be message drop here because the message is full from one, which has been filled from one queue, and it doesn't have space for other ones. So you could possibly drop message, but that would mean interference. You have flow control, same priority blocking, increased delay and buffer, but if you are good here, you would not include any ingress and any interference here, so this seems to be something you can handle. However, you have few queues, and as a consequence, few priorities, so many of the original priority levels on the CAN bus have to be merged into typically 4 levels. And that means you can have same priority blocking on one level, but the background is really different priorities. Because you are forced to put different priorities into one queue, you get blocking suddenly, which was not intended originally, and will not happen on standard Ethernet if you use it properly. Now, this is the indexing issue, which surprisingly you find in existing switches. So here's the destination address space, which is globally assigned typically, provided by IEEE. Or if you don't want that, you can use your own space, then as a private space, then you have to translate that if you go to the outside. There are a lot of issues with that, I'm not touching them further. The thing is here, you have certain areas here which you give to different suppliers and different OEMs. And what happens, however, if you access the forwarding table, it uses hashing to be fast enough. And the hashing has a limited index value space here. And from here you access the table, which is typically a set associative implementation. Now, if you have, for example, these two critical messages, which go into 2 ways of the same memory, so they are not conflicting. Now let's assume there's another one coming up. This could be anything. Some other address here, which could be an infotainment address, goes in here, has a conflict with that element here, with the red element here, and moves it out of the forwarding table. That by itself is not a catastrophe, but the next time you get the critical message again, the system will start with a broadcast and find out where the address is. So this is a serious violation, and we've seen that these things actually happen in many of the indexing spaces, and it's almost impossible to completely avoid that. So you have to be very careful what you do with the indexing space, and it is not standardized. Next thing is the gateway. Let me speed up a little bit here. A lot of things to say. The domain gateways. Now, they also have an influence because they have to package all the data which come here and then send it to other places. How can we do that? That's a little bit busy slide here, but you will see in a second why. I come from a signal, then I put it into a CAN frame, send it over the CAN bus. Then from there, I go to the domain gateway, which is here, and then generate an Ethernet frame. Then I send this over the Ethernet, and on the other side, I unpack it again. So what does this mean? Now let's assume you have all these messages here. There are different colors on this bus. They are multiplexed to different frame groups, and the frame groups are responsible for example, different priorities, or to build up frames, which are then, when they are triggered, put into a larger frame and then send over the Ethernet. You package many of these small frames into larger frames. Why do you do that? It's shown here. Because you would like to save traffic here by not sending each and every CAN frame individually over the Ethernet with all this extra effort here and all this overhead. And the same thing you don't want to do with the camera traffic. And therefore, you have different ways of frame grouping. You can group them by destination, so you put all the frames together which go to one destination here, or you can group them by priority, meaning you only put things together which have the same priority. You can do this for period and for deadline, so they're with same deadline. So many possibilities, and they're all permitted. And you see here what could be the difference here. Here you, for example, go by deadline. That means you have to send one package to different, or one of those frames here to different addresses. Okay, so what does this mean for interference? Let's go back to our target here. Buffer timeout is defined by AUTOSAR as one standard. That means the frame is sent priority, and that means here we would not have frame interference because it's periodically sent. Here we are safe. There's the buffer full event, meaning when the buffer is full, the whole thing is sent out. And this, of course, is interference, because now it depends on which frame comes when to identify when this frame is sent out. Or the so-called trigger frame, that means certain CAN IDs immediately release the frame, the rest does not. This is an interference, because it means that possibly you sent the data earlier now than usual. And there's a per frame timeout, which is also there, and that means you can send it upon a single frame, but this is a simple case. You see here in the packaging domain, we again have a source of interference. We have to be very cautious, and remember, it's deeply embedded in the adapter. Okay, so what do I conclude here? There are numerous sources of interference, right? They are handleable, but you have to take care. Here is, one less. Switch operation, prioritization, frame grouping, triggering. There are no standardized solutions here. In contrary, the standard leaves everything open and leaves it to you. They are partly based on non-disclosed parameters, so the indexes of the switches can only be received by an NDA. You have to make an NDA with the switch suppliers because they don't tell you. If you buy them from the market, you don't know how the index works. So it means you need careful evaluation and design, and please don't rely on the standards only. See what the differences are. Now, I assume that systems are working correctly, no problems whatsoever. One step further, when we go to autonomous driving, when we go to safety critical operation of complex functions, interdependent functions, then we need to have to look at errors. And I'm focusing here on hardware fault errors, not on possible standardization errors. So what are the hardware fault probabilities? Now, if you look at the published data, you will find the following. Here is a transient, intermittent faults. Here are the permanent faults. And the question is, what is the critical thing to look at? And what you can see here from the data which are published, that you have because of the bit error rate, approximately 10 to the power of 2, meaning hundreds, of errors per hour in car. So that means you have, at this point, you get lots of errors on the communication wire, which are all transient. And it's clear, you have electromagnetic interference and so on. You already had them in standard CAN communication, but CAN had a very good error protocol. Error protocol, how about here? Sorry. So this is the most frequent error. The other ones are not so frequent. Computation has a wide variety, and this very much depends on the quality and the protection which you use in your microcontrollers. So I'm not going to touch on that. And the other ones are quite rare. The permanent errors on communication wires, and that's what we're looking at here, are rare, and also the computational wires. I will have a short look at them in the end. But currently I'm going to focus on these ones. The consequence of that is an error on this level must not be treated with a fail-safe operation, because it just happens too often. Your car will permanently stall several times an hour. So an error on the communication link, like it is used today, is something which is part of the normal operation. It must be part of the operation, so all error protection must be sitting here. For the transient errors must be sitting directly in regular operation. So this is what I said here. Now, what does this mean? Now, in bus operations, we already had that. But now we have end-to-end communication here. And the question is, what is a good way to handle transient errors on this way? And Internet had these problems from day one, and Ethernet also. They also use the noisy environments and have to react. So the idea is to see what they have been doing. And what we suggest here from that study is to use end-to-end error control. Don't even try to fix errors here. Only go from end to end. So this way you don't need to touch the switch. The switch is allowed now to drop errors, drop data, and this can also be done, by the way, by message dropping. So the protocol which has been proposed here is the automatic repeat request. So this is an extra function which is sitting here at the terminal nodes. To give you a quick idea how this looks like, and we need to look at that to find out how much timing error overhead we get this way. How much does this protocol slow down our timing? And CAN uses a stop and wait protocol. This is really slow and is only working on a bus. We need faster things. And here what we use is go back N. It's used already in some other standards. But the idea is you send several data before you stop the whole thing to wait for the next acknowledge. And the longer these packets are, the less overhead you get for waiting. But the more you have to repeat when there is an error. Now the error is rare, right? This is important to understand, that the error is very rare, so the normal operation should be optimized. You have the error protocol, but you are basically backed up by the error protocol in case there's an error. So this is again the BMW example with a two-switch configuration now. And here we apply now the ARQ with two sizes, step back 5 and step back 10. Of course, the 10 is faster in normal operation, as you can see here, because it has can transport more data before it switches back. But on the other hand, it will have a longer time to recover from error. What I want to show you here is this is a formal analysis, and we can guarantee these data in normal operation, even though this is an acknowledgement protocol. This is progress and timing verification that we can actually handle and guarantee these things. So this works. So the transient error can actually be handled end to end. Now my last step here, and then I will conclude, is the question of what happens if one of the switches here really fails or the link breaks. This is a rare event, so here we want to ask whether a fail-safe operation or a fail operational mean a short time to reconfigure. There are several ways to do that. TSN proposes multipath routing, which is very flexible and is very universal because it has no extra delay, but it has a permanent overhead because you have to send the same thing several times. There's also automatic path detection and routing, which is the standard approach in Ethernet. Ethernet is an everyday, such a broken link is an everyday problem, but it has a large and unpredictable delay. It doesn't work for us. So we need something else. Unfortunately, recent research has led to software-defined networking. Software-defined networking, which is also proposed for high-loaded internet applications, such as for search machines and so on. Introduces a control plane and uses a widely published open flow protocol here. Question is this fast enough, this configuration? I give you first results here. We made a feasibility study. This is from another OEM configuration here, and we used a central SDN controller, and we actually could show that such a system here can have access protocols of 1 to 6 milliseconds, and if it's pre-configured, if it switches between pre-configured error situations, we can bring it down to less than 2 milliseconds. So that seems to be acceptable. If this is sufficient, has to be decided for a given automotive function, but typically that should be enough. And there's, however, further research needed as we do this, for example, in the Cephur project, where, for example, TTE Tech is also involved and others. Let me draw the conclusion. Now, there are many new features here in Ethernet introduced in TSN. They addressed interests from many industries, industrial, automotive, media. They're all working together in the standardization here. But some of the additions, because of this variety here, seem to be redundant compared to what we already have in AVB, such as, and we could show that in peristaltic and burst limited chambers. For automotive applications, now specifically taking, the minimum end-to-end latencies which can be reached are typically 1 to 2 milliseconds, which for most applications, so we know so far, is enough. It's feasible with AVB, or if you like, you can use AVB with additional preemption. That might be a good idea. Clock synchronization is already used in 802.1 AS. I'm not sure if you need the other ones, the extensions. We have to see, but we have a good start already. What I would like to point you to is that these additions increase the protocol and circuit complexity, and this might cause problems with certification agents when they have to certify the switches. So it might be wise to come up with a subset which you really need for the different domains. Okay, and the switch costs, so please be selective when it comes to new switch features. So let's look at the design complexity issue again and the cost. So the cost of ownership trap. I said one of the motivations was to get rid of the cost of ownership, but we have many more parameters here in variance than in current networks. And that means we have to work on MAC address management, switch management, protocol selection, packaging, and so on. For us as university and working with industry, it's nice because we get a lot of contracts to investigate these things. But on the other hand, it increases the cost and the variety. And the new standards in TSN even increase feature set. Now, the current software standardization does not limit variety, so we have to find something here to limit the variety, to bring the cost down, cost of ownership down, and TSN unfortunately doesn't help very much at this point, even though it is very helpful in other aspects. We have seen that we need probably unified automotive solutions, avoiding incompatibilities and as a consequence extra cost. So the cost of variety management at all levels generates new cost of ownership for automotive industry, and I think this will be the same for industry as well, where you have several standards. Okay, I conclude. Ethernet is a viable basis for automatic driving. We have adaptable bandwidth and latency, we have predictability for hot real-time systems, flexible end-to-end control, and we have extensions for resilience and test configurations. However, there are many traps. So we need a highly systematic approach to mitigate the risk, taking all these issues into account. And we have individual solutions, but they need to be brought together. And research should really address the remaining issues here, such as bounding interference on all levels, not only on time, but also others. Analysis for end-to-end timing, for worst case and others again, and predictable dynamic network control, such as software-defined networking. Thank you for your patience, and I'm happy to take questions.
Thank you for the very exciting presentation. Questions? Yes.
Hi, thanks for the great talk. While I was going through your presentation, I was wondering what are the main reasons why, given your constraints, you wouldn't use something like AFDX, which is effectively based on Ethernet, so you have the old bandwidth benefits, while it also solves the problem of the bandwidth control, and you have, well, static crowding in that case, and you can analyze it using something like network calculus.
Yes, exactly. So let's start with the last one. What we're doing here is similar to network calculus. Most of the approaches currently used are more or less related to network calculus and busy window analysis. Those are the two main tools which have been refined over time. Why don't we use AFDX? Well, automotive suppliers want very high variety and very high load capabilities which you have. And typically in AFDX, as it stands today, if you look at what really is going through the system, they are controlled at the boundaries, and that means you only get a limited maximum load on the system. This is the main concern. The second concern is that AFDX actually uses a virtual link paradigm, which introduces a slight difference in the Ethernet standard. The VLAN field is changed. But it has been considered, I should say that, has been considered but not further pursued. But maybe things are brought together on that level. I think it's a utilization constraint is the one, and then it's the cost of guarantees, giving guarantees, because it's a del A. If you know FDX has del A specified, you cannot do that with this network. Only part of that can be specified like that, because people want to mix and match and incrementally design. So the design style in automotive is just far away from aircraft. I wouldn't fly in an aircraft which is designed like a car. Just too complex.
Do we have further questions? Yes.
So thank you very much for the very nice talk, and I really appreciated to see at the end your connection to software-defined networks, because it's a hot topic in general purpose data networks, and it's one of the approaches that is being followed nowadays even in data centers and things, where we really want to detach the control from the data path, right? And one of the problems that we've always had is that the control is actually dispersed by all the equipment that makes up the network, right? And this is a problem. So when we concentrate the control of the network in an entity, this really simplifies what we can do in terms of control of the packets and the data flows. One of the problems that I've been looking into that recently, and one of the problems is that SDN as it is does not consider timing. And there's no support that I know of, for example, in OpenFlow for real-time communication. So how easy do you think that we can include that support into SDN?
Well, in this particular case, we invented our own small protocol, which was predictable. If you have an arbitrary software stack on an SDN, then this will not be so easy. But you just mentioned a very important point. It's the use in data centers. The data centers also depend on predictability, because if you run a map reduce algorithm, you want to know when the map is done, and you want to know when the reduce is done. And therefore, I think interests might actually converge.
Do we have further questions?
So I'll still be here, so. Oh, one more.
Okay, thank you for your talk. And your focus of your talk was mainly focused on the runtime environment, right? So, and if we take a look to this new capabilities of TSN or SDN and so on, we are running in a much more complex world also at this level. Isn't there a need also for advanced techniques for the configuration and maintaining of such systems in terms of management tools?
That's another 1 hour talk. Excellent question, because this is exactly one of the solutions we have. Because what I didn't introduce here is the dynamics. People increasingly want to change properties of the system runtime. Adaptive AutoSAR, which is a new buzzword in the automotive industry, tries to give some more dynamics. What I showed, some IP, same directions. You get dynamics in the network, and as soon as you get dynamics, there is no designer around. Right? So you have to find out what you can do this way. And I think auto-configuration and autonomic approaches like people at IBM had developed that many years ago in the autonomic computing project. If we go this direction, there could be the next golden egg, maybe.